On a rainy night, we will talk about something where it never rains. I'm going to talk about something tonight that is a subject of my research, but not a subject of any of the things that you talked about. But it's sort of a circuitous path to getting to it. When I was a graduate student, we built a telescope to look at auroras, not on Earth, but on Jupiter. And I spent 5 years building that experiment, and we took it out to the White Sands Missile Range, and we launched it, and it went up, and it performed flawlessly, except for the part where NASA's pointing equipment failed, and we pointed at a random point in the sky as opposed to Jupiter. We were incredibly disappointed about that, except that later on when we were looking at our data, we found this tiny little signature of something, and we realized that we were looking at the signature of the big boundary. And even though I was not involved in that area of research at the time, when one wants to graduate, one becomes an expert in whatever is necessary. So I learned all about it and became fascinated by this structure, which is the largest structure that defines our planetary system, and actually more than just our planetary system. It's a big story, though, so it'll take a little bit of background before we go through that. So I'm going to talk a little bit about what goes into making a boundary of this size and how it starts from the innermost part of our solar system and goes all the way out to the outermost part of our solar system and well beyond that as well. So to start with this, our context is a dark square. And it takes a little bit of imagination to fill this dark square. But this dark square happens to be a sleeping astronaut. Now he is laying in his bunk. He is in space for the first time. He is floating around, and he's thinking, well, this isn't so bad. I'm not all that nauseous. Space seems pretty good. And then he sees these things, flashes in the darkness of his eyes. And I've talked to astronauts who have experienced this, and they never tell the new astronauts that this is going to happen because it is so much fun to see if they can figure it out. What is happening is very energetic particles are hitting their eyes. And as they go through their eyes, the interaction of those particles with the fluid in their eyes is producing a characteristic type of radiation called Cherenkov radiation, which is blue. And they're seeing flashes. Their eyes are like a Geiger counter. They're counting the radiation in space. And they are also counting down how long they can stay there. Because last I checked, when I go to sleep, I don't see that. So being down in the surface of the Earth protects us. But once we're in space, we have these charged particles, and they're everywhere. So the astronaut has to contend with these, and it's a large part of the reason why people tell you that we can't go to Mars in the short run, because the farther away we get from Earth, the more of these particles you run into. And the more of these particles you run into, the more of things, not your eyes, that they can damage, they run into. And eventually, you accumulate a dose of this material enough that it begins to affect your health, and if you stay up there long enough, your health is over and you die, which is why people don't go to Mars, or at least NASA isn't sending them. Now, they go in the movies all the time, but generally they don't make it back because something eats them, which is good because the other way is bad. So these particles are the dominant environment in space. It's not an empty place. When we talk about things like comets, they're incredibly rarefied objects. The individual atoms and molecules in a comet, they don't actually collide with each other. They're so rarefied. But most of space is beyond that in terms of there not being anything in it. And much of that is dominated by these charged particles, and they are not safe at all. Anytime, you can get hit by one. Now, all of these charged particles fall under the broad classification of what we call a plasma. Now, many people talk about plasmas as the fourth state of matter. And in many ways, it's really true, even though a iron charged particle is still iron, a hydrogen charged particle is still hydrogen. The elemental characteristics of an object that is a charged particle don't necessarily change, but boy, does everything else about them change once they become charged. And that's why we call it a state of matter plasma. Plasmas are composed of charged particles, and we see plasmas in our daily lives. I mean, you can get a novelty toy at Spencer's Gifts that will show you one, or you can just wait for one of these storms, and the lightning will show you what a plasma looks like as well. Plasmas are composed of charged particles. And we know what most of these charged particles are like. Most people learn about these in school. There are two types of charged particles. There are positive charged particles, and there are negative charged particles. And that has nothing to do with their point of view. It just has to do with the fact that charged particles come in two flavors. And as a basic rule, positive and positive push apart, positive and negative pull together, and negative push apart. And the force between them is incredibly big. In fact, it's so big that compared to the force of gravity, the electric force on a per mass basis for a proton or an electron, which is the negative charge, is 1 with 32 zeros after it times the force of gravity. So as a result, charged particles tend to occupy their own little universe. If there is something involving an electric field, or as we'll see in a minute, a magnetic field, gravity no longer seems to be much of an issue. 10 to the 1 with 32 zeros would tend to indicate that. So the environment of space where all of these charged particles are flying around is one that is largely devoid of thinking in the terms of these particles about the gravitational forces that are around them. They think about each other, and neutrals think about themselves. And there's all kinds of interesting physics that happens as a result of this, everywhere from inside our atmosphere into the space around the planets and all kinds of scales. And I'm not going to really talk about most of that. I'm just going to talk about the biggest scale on which these things interact. Now, the other protagonist in this is a magnet. Now, magnets are kind of the yin to the yang of electric fields. They're very deeply related. You know they're deeply related when you refer to light as electromagnetic radiation. So if you've taken any physics, you know that electric and magnetic fields respond to each other. They're inextricably linked, even at a basic level. But if you think about a magnetic particle, it's not like a charged particle at all. It has both of its charges, both of its senses on itself. That is, there's no such thing as a positive magnetic particle or a negative magnetic particle. There is a magnetic particle with positive and negative, or as we call them, north and south. And you can get all kinds of organizations of magnetic particles with fields of varying sizes and shapes, but the simplest of them is what we call a dipole. That's what most people think of when they think of a magnet. It's just north, south, and the lines of magnetic force, the field that joins them, flow between, just like this here. And a simple example of a dipole magnet is our planet. The Earth is a dipole just like this. Well, not exactly, but it's pretty close. And we have a north and a south pole, as anybody with a compass can tell you. There are other types of magnets that have many poles, and it depends on how they're organized. But this simplest of magnets is the thing that we're going to work with here to talk about the big boundary. So if we put charged particles and magnets together in one place, we get something very originally called a magnetized plasma. We should come up with a better name that sounds cooler, but this works pretty well. And the very interesting property of charged particles and magnetic fields is that they tend to respond to each other in movement. That is, an isolated charged particle that is not moving at all doesn't respond to having a magnet near it. And it won't unless it starts to move. But if it starts to move, it will notice that magnetic field, fall in love with that magnetic field, insist on always being with that magnetic field, and it will be with that magnetic field by orbiting around it, a gyration. And when that happens, the particle becomes trapped on a magnetic field. And since in space and pretty much everywhere, there's no such thing as something that is not moving at all, generally almost all magnetic fields and charged particles wind up with some kind of association to each other. The interesting aspect of this is that the motion of the charged particle is perpendicular to the direction of the field, and the direction of positive charges and negative charges are in opposite directions. That makes for some very interesting properties, and the charged particles that are hitting your eye when you're in space, a lot of those have been hovering on field lines, holding onto them, rotating around until they hit some poor guy's eye and turn into Cherenkov radiation. This relationship is so fundamental to space physics that it's impossible to talk about anything that happens with charged particles or magnetic fields without this relationship. And it's very important for us as well, because this relationship also provides us with some protection. We'll see. And it leads me to my next point, which is, so what with all of this? I haven't talked about any boundaries yet, and I'm sure that's really bugging you. But we have set the stage. We've cast the play, and now we can take a look at it. Now, the big boundary is way out there, but it has two players. One of them we know extremely well. The first one is our sun. Now, the sun, when you look at it in visible light, just on an average day, can be a fairly featureless object if you can stand looking at it for more than a tenth of a second. But for a very long time, we've known that the sun can develop spots, dark regions on its surface. And this is a great picture of some sunspots. Now, these sunspots look very dark. They're not actually dark. The sun is about 6,000 degrees Kelvin, which, for reference, the boiling point of water is 373 degrees Kelvin. So we're talking about hot, pretty hot. These guys are still about 3,500 degrees Kelvin. If you were to take a sunspot, move the sun away, and put the sunspot out in space, it would be so bright you couldn't look at it. It is only against the glare of the sun that they look dark. But something is happening to make them be spots. And because of all the time I just spent, you can safely assume it has something to do with magnetic fields and charged particles. And so it does. Now, the other thing about sunspots is that they're periodic. They're not there all the time. Now, you would say that looks kind of random, but it really isn't. If you go back in time and you measure sunspots, you find that sunspots change in the amount and where they're found. And this is very interesting. So you start off, let's say back in 1880, so we've been doing this a while, and you see sunspots, they're 30 degrees away from the sun's equator, to the south or to the north. And as time goes by, they go moving down toward the equator of the sun. If you go back and look at this last picture, you can kind of see it, right? There's kind of an angle here, heading down toward the equator. And these guys are already there. So you can kind of guess this picture is at the end of that cycle, and it is. Now, the other thing about it is, if you take a look at this using a technique that allows you to measure magnetic fields by looking at light, called the Zeeman effect, you can actually tell that these sunspots are regions of incredible magnetic force, and that they're poles of a magnet. So if you look at two sunspots, very often one is north and one is south, which means they're connected like a dipole. So if you could look above the surface of the sun, you would think that you would see this loop of field, right, going from one to the other, like in a dipole. And we've also noticed that every 11 years, the poles flip. That is that in 1 year, the north leads the south. The next time, the south leads the north. Every 11 years. 11 years, starting up here, down to here. Boom. Starting down here, go to here. Up to here, down to here. And if you look at this down here, you can see the number of sunspots banging up and down. And we learned a long time ago that that number of sunspots banging up and down is directly related to the frequency of auroras on Earth, solar storms, all kinds of things. So these sunspots are really telling us something about a magnetic environment that is directly relevant to Earth 150 million kilometers away. Well, if we look at the sun a little bit more closely, we start to see what might be going on. Now, this is an image of the sun looking at a specific wavelength of light that corresponds to hydrogen that people are very interested in because the sun is mostly hydrogen, which means it should be easy to see. And during the periods when the sun is really active, you get all of these interesting features that you can see in this hydrogen light. This up here is called a loop prominence. Now, having seen the sunspots and having me tell you they're north and south, and it's like a dipole, you can see the dipole, right? You're actually seeing it. And what that means is that there's hydrogen trapped on this. Now, the sun is 300,000 times bigger than the Earth, so it's got some gravity. But these charged particles happily hang above the surface of the sun like they don't even know it's there. And they don't. They're held by that magnetic field. And you can see these dark bands called filaments that are extending across the sun. There are other prominences that we're just not looking at on the edge. So on the sun, as we go from the beginning to the end of this really active cycle, we are creating these magnetic flux environments where huge amounts of plasma is trapped on these fields. And you have to imagine that that's going to do something. And it does. Now, every once in a while, you'll get something really big that happens on the sun. And this is an old movie, but it's one of my favorite movies ever of the sun. This is of a prominence way back in the 1940s. And what it's doing is it's flinging itself off the sun, isn't it? And if you look closely at it, you can actually see twisting, torquing of the magnetic field as it does that. You can see spiral patterns in what's going on. We've known about this for 60 years. And today we recognize that something like this is usually associated with what we call a coronal mass ejection. And there was recently a report that we were going to get hit by a solar storm, and they often refer to it as a CME, or a coronal mass ejection. Now, for perspective, this dot is about as big as our planet on the scale of this picture. So when that thing goes flying off, it's releasing a lot of material. And all of it is charged particles. And those charged particles are loving the magnetic field they're on. And as they go flying away, they're saying, you can't stay here. You must come with me. And so they grab the magnetic field of the sun and they drag it out into space. And those charged particles are moving away at 100 to 1,000 kilometers a second in our direction. These are incredibly energetic events. Now, the kicker to this story, and why it matters to the big boundary, is that the rate at which these things happen is tied directly to this idea of where the sunspots are. And if you look at the sun, we can explain why this happens. Now, the sun is not a solid. It's not like Earth. It's a fluid body. And fluid bodies don't rotate all at the same rate. The equator is rotating a little bit faster than the mid-latitudes, which is rotating a little bit faster than at the poles. And as a result, it's actually stirring its interior up. It's dragging its bulk around. And because the magnetic field inside the sun is bound to the plasma inside the sun, as the plasma gets dragged out, so does the magnetic field. And so what happens on the sun is every 11 years, it makes a new magnetic field. And then this motion, just like a batter who has one of those rubber band things which you hit, he hits it, and it goes, wraps, and then it unwraps. And that's what our sun is doing. And when it is most wrapped up, that's when you get the coronal mass ejections. Our sun's magnetic field is currently all wrapped up, and that's why we have to worry about these things right now. Now, for the big boundary, what this means is that in addition to these coronal mass ejections, what you're also getting is a background of just charged particles leaving all the time. All the time. We call this the solar wind. And we've understood about the solar wind for 50 or 60 years. We didn't really get all of its characteristics until we put all the pieces together, and we sent a bunch of spacecraft out into space, which initially didn't fare so well because nobody had any idea they were going to face this. And now we have a much better look at what goes on. Now, the basic characteristic is that we get these features called streamers. They're sending material out. And you can get this one right here. Looks a little like a pith helmet, you know, like the old German helmet. They call that a helmet streamer. We were able to study these for a long time, only very sparingly. But about 1996, we put up a satellite called SOHO. And SOHO had special cameras that could block the sun and look at the sun in ultraviolet light, where the sun wasn't as bright, but these emissions were. And so they were able to take a look at what the sun looks like on an average day. And so that's what this movie is here, if it plays. So this doesn't cover a whole lot of time, just so you know. Keep watching the date down there. Aren't you glad you're down here? I'm glad. You mean the little flecks? Oh, does this one have a comet? It might. Hold on, let's look again. This is worth watching more than once. Actually, it's one of the other things SOHO discovered is there's a whole group of comets that just want to do nothing but fly into the sun, and no one had ever seen them before, and they started watching them, and there's some great pictures where they fly into the sun and then something flies off the other side, which is completely unrelated, but very funny. What you do see here are these streamers and all these things. This is only 14 days. And remember, the sun, which is this dot right here, is 1.4 million kilometers across. So the speed and energy of what's coming off of the sun is immense, immensely powerful. And the other thing that you'll notice, I'll play this one more time just for the heck of it, is that every once in a while you'll notice all those streaks. That's SOHO's camera experiencing the astronaut effect. Charged particles are flying into the detectors and creating this noise, these flashes of light that it's seeing as though it was actual data. So you can kind of tell when things are bad at SOHO, and you can tell when things are good at SOHO by the number of those flashes that are happening. And just for reference sake, SOHO is hovering right in front of Earth. So whatever happens to SOHO happens to us very shortly afterwards, about 20 minutes after that. So you can look at that and say, well, this would be bad for the Earth. But it's not fully bad for the Earth. And the reason it's not fully bad for the Earth is because of the first boundary. When all of that material comes flying out, it's carrying the magnetic field of the sun with it, because it wants it. Particles are spiraling around that field. And 150 million kilometers away, it notices a dipole field from our planet. And when it notices that dipole field, it moves around it. It's like a rock in the stream for this collection of charged particles. Some of them find ways to sneak in. They'll come in through this little cusp region here. They might connect back in the tail. But for the most part, the solar wind hits the Earth and goes around. And that's very important, because if it didn't do that, then it could maybe hit the top part of our atmosphere and maybe start to grab it. It could maybe make more plasmas and take those away. And there are people who think, and probably with good reason, that that's a large part of why Mars's atmosphere is the way it is, because Mars does not have a magnetic field today. Now, the reason why this happens is the side aspect of how much charged particles love magnetic fields. They love them so much that they won't share them. So if you have a plasma that is bound to a magnetic field, and it encounters a plasma that is bound to a magnetic field, they have a magnetic discussion, which is my field, it's better than your field, you can't have any, and vice versa. And so two magnetized plasmas hit and move apart. We call this a discontinuity. And you can get all kinds of interesting phenomena, because if one plasma is coming in at 1,000 kilometers a second, it's got to stop by the time it gets there. And they're actually moving fast enough within the fluidic nature of the magnetic fields that they're supersonic. And so they will slow down, create shock waves, and then they will decelerate and move around. And then you can have all kinds of connections between the fields. It's a rich, dynamic environment that is really amazing to look at. And every planet with a magnetic field in our solar system has its own way of addressing the presence of this solar wind, which is increasing and decreasing as a function of time over this 11 and 22-year cycle. It's a big boundary at the Earth. It's many, many times the Earth's radius, but it's not the big boundary. To see the big boundary, we need to start looking out into space. And these are some pictures of stars not very far away from us. And these stars are embedded in our galaxy. And you can see, for instance, and I love this picture, this star right here, if you'll notice, there's this wave around it and a tail going back. And the wave extends well off. It's up all the way over here and all the way down there. And you can see this star over here has a huge wave out in front of it. And this star is so awesome because it has the wave here, and then it's got all of these blobs of things going out behind it, and all of those are plasma. All of them. And what we are looking at here is that shock. Something is impacting those stars at very high velocity, decelerating down to meet something that it can't mix with, and in the process producing a shock wave and a density buildup and a flow around, just like Earth, only much bigger. So what's causing that? And that's a very good question. So it turns out that the sun is not the only source of magnetized plasma that we know of. The space between the stars, our whole galaxy, is composed of a combination of neutral gases, mostly hydrogen, some helium, some heavier species. Things like water and carbon dioxide are present. Often it's very cold, sometimes it's very hot. It's mixed in with some dust, and you can see it. It's this brownish material all over our galaxy. And a fraction of that material is magnetized plasma. And we call this, collectively, this material, the interstellar medium, because, again, we don't come up with fancy names in astronomy. And the interstellar medium has all of these structures around here. Now, here's our star, and you can see these features around here. These are other nearby stars. And this distance here is about 120 light years. So big, massive scale, big boundary. That's what we're going to get. And so we can predict it. We're embedded in the interstellar medium. We look at other stars. We see the shock wave. We have to have one, don't we? We should. And it's going to look something almost as cool as this. And almost as cool as this says something very interesting. This is our star. Here are all the planets. Here's our demoted planet out here. It's very sad. Don't ask me if I agree. And then extending way out beyond that, we think, is more of the sun, continuing to expand out into the galaxy until coming from this direction, whatever direction we happen to be moving in, is that magnetized interstellar medium. And out here, there should be a deceleration coming up against a deceleration in here and a discontinuity, creating a gigantic structure called the heliopause, the big boundary. And it's a great theory. The idea is that our big boundary should have certain features. We have in here our sun, and it's producing all of these charged particles. You've seen them. They're very nasty, and they're moving out at 1,000 kilometers a second, so that's really fast. And they continue out until they start to notice up here there's a magnetic field they do not like. And it doesn't like it either, and so it starts to slow down, and when it does, there's a shock. We call it the termination shock, which sounds very dire, but they continue moving after that. And they keep moving until they hit this point, the heliopause, at which point they flow back and out down into a wake region that looks very much like that blob of plasma that we saw on that one star. Coming in the other direction is this other plasma, and how fast it's going, we don't know at the beginning, and it starts to decelerate. It too goes into a shock, maybe, and then it too stops and flows around. Heliopause, big boundary. That is a wonderful, wonderful theory, and you now understand why it exists and where it probably exists. And I point out again, all the planets in here, big boundary out here. So this is more theory than observable at this point. The structure of these things is such that it's at some distance as much as 100 times as far away from the sun as our planet. So I said our planet is 150 million kilometers from the sun, so go 100 times farther than that. That's several times farther than Pluto, very, very long. And we formed this big area, and it leaves us with many questions. Do we know what the properties of the plasma are coming in? We kind of know what the solar wind is. We can model that. We can see it. We can measure it. But what's it hitting? You're going to hit something. You better know what it is. Otherwise, you don't really know where that boundary is. The other thing that we need to know is how fast are they going? We know how fast the solar wind is going, but we don't know how fast the sun is going with respect to the interstellar medium. The interstellar medium has to be coming toward us or going away from us. If it's not moving, if it's moving at the same speed, then it's not going to be an interesting reaction at all. And lastly, if there's a magnetic field in the interstellar medium, and there is, where's it pointed? Are the magnetic fields going to be like this? Are they going to be like this? Are they going to be like this? All of those play into the shape of that boundary. It drives theorists crazy because it's unconstrained. You can make up any boundary you'd like and then argue about it at meetings. It really makes them for very interesting talks. All right, so how are we going to determine these things? Well, I told you one way we could determine it. Have a graduate student fail to see Jupiter with his rocket. And we saw this because of a phenomenon called charge exchange. And the way this works is I told you that part of this is plasma, but a lot of it is just neutral hydrogen. And as this neutral hydrogen comes in, it notices this big collection of plasma up here. What it doesn't notice is this boundary. Neutral hydrogen could not care less whose magnetic field belongs to who. No, it doesn't care. It lives in a world where it cares about gravity, where it cares about pressure. Not these guys. So they're stopping. He's going through. And in this big, dense place where all this plasma is located, every once in a while, as that neutral particle goes through, it'll swap places with one of the plasmas. A charged particle will become a neutral, and the former neutral will become charged. And as a result, this guy who was slowing down now goes right through. And so when we look at the hydrogen coming into the solar system, we can see that part of it is slower than it's supposed to be. And that's the trick that we did with my rocket. We looked at the velocity of the gas that was coming toward us, and we could see the signature of this boundary, this transition across here. We, from Earth, were looking 100 times as far away directly at material coming into our solar system. I, unfortunately, was not the first person to do this. I might have thought I was at the time, but in fact, it was a really old measurement way back in the 1950s by really famous Jack Brandt and Chamberlain. With the same basic technique, we're able to see this effect. And so we've known about it for quite some time. What they couldn't really do from this was tell what the conditions of the local interstellar medium were, because all you were really getting was how much it was decelerated. But what was the velocity when it started? So they went ahead and posed the question, and people began to try answering it. Now, it turns out there's a really easy way to answer this question, and that is if there's neutral gas between you and something else, if you just look at something else and measure how much that gas scatters of the light that's coming from that object, then you kind of know how much there is. And we started to do that. So you would go and you would look at a star that's 20 parsecs away, and you would measure the amount of absorption between you and there, and then you would say, let's suppose all of the gas is uniformly distributed between here and there, which is crazy, but let's do it. Then we can say how fast and how dense that gas is. Good. No one believes you, so you go and observe more stars. Early study, the first real major study, they looked at 270 stars in all directions. And they found that while there were variations in the density around our star, they could break down the interstellar medium into a series of clouds of different temperatures, densities, and velocities with respect to our solar system. And they identified us as being right on the boundary between something called the local interstellar cloud and the G cloud, neither of which sound very interesting. They need better names. And, but we're heading into the direction of the G cloud. That is, the G cloud is moving this way toward us. And the velocity was about 25 kilometers per second, relative velocity. So that gave us a very useful number that we could use to then go back and say, okay, we know how much the plasma is moving. We know approximately how much stuff is decelerated. People began to generate models. And then along comes SOHO. Now, I showed you the movie from SOHO, but SOHO also has an experiment that I'm sure was inspired by my rocket, because I want to be the reason. And its instrument is looking at this hydrogen. And it had an instrument, it's gone now, but it had an instrument before it broke that could measure the velocity. So this is a picture showing all over the sky measurements of the velocity of it. And it's going faster toward us here and away from us over here. So they were able to just see the flow of this material through. And by looking at the deceleration, they could see that it was getting slower in this direction, faster in this direction, and that it wasn't quite symmetric with the direction that we thought the interstellar medium was coming. And so they realized that what's probably going on is that the difference in the direction and the velocity difference means that that's from that magnetic field. So instead of having magnetic fields that are like that, the interstellar magnetic field is tilted. And as a result, when it hits our our solar wind moves plasma down along the field, which increases the density in one direction, so you get more deceleration and a deflection that we could measure using this experiment. It's a really fascinating way to use something really minor to get at that. Now, this reigns supreme in the measuring the heliosphere world for not long. Because very shortly after that, a new spacecraft went up. And this one is a really cool one. This is called the Interstellar Boundary Explorer, or IBEX. Now, IBEX is a very simple experiment. It uses something called an energetic neutral imager, or analyzer, which sounds really amazing, except that it's essentially a piece of tinfoil, two pieces of tinfoil, and when something hits it really hard, they can detect the two hits, and the separation between them tells them the angle. So it's a really simple experiment. But they suggested that particles coming across this boundary might have a lot of different energies because there's all kinds of things that could be happening. And boy, were they right. So the first thing that they did was they did these observations, did an all-sky map, and they measured all the energies of what was coming in. And they published this picture, which if you ever run into anybody from the IBEX team and they tell you, oh yeah, we knew that was coming, just laugh at them, because they didn't. This was a big surprise to them. They call this the ribbon, and the ribbon is this place where there's incredible amounts of high energy charged particles coming into our solar system. And the cool part about this is that those charged particles are following the point where that magnetic boundary is touching our magnetic field. It's the equator of that magnetic field sitting against there. And what's happening is that process that's producing the hydrogen atoms I see, well, they come back into the solar system, and then they exchange again with the solar wind. And then out comes the solar wind, and it exchanges again, and it comes back, and you have this energy back and forth like a mirror, and it becomes a little bit like a laser, and it produces these super energetic particles that come into the inner solar system that they can see. So they were able to use that to come up with this fantastic model for the heliopause. We have the magnetic field that's like this, and we have our boundary, the heliopause, like this. You're pushing plasma this way, and so our heliopause should be tilted on its side. It should be farther away up here and further in down there. We could be done. We might have it. There's only one problem. How do you tell? You can look and you can see the deflection of the hydrogen and the neutrals. You can look and see the magnetic field. You can even see the ribbon. But the ribbon itself isn't telling you where those particles are coming from. It isn't telling you about the shape of that boundary. So we needed something else. And we had it. We just didn't mean to have it. Voyager. We launched the two Voyager spacecraft in the late 1970s. Voyager 1 went to Jupiter and Saturn, and then kept going. Voyager 2 went to Jupiter, Saturn, Uranus, and Neptune, and then kept going. And they've kept going, and going, and going. And they have these little radioactive generators on them, and the radioactive generators are slowly decaying, so they're not doing as well as they used to do, and most of the experiments on Voyagers 1 and 2 have been shut off. The last thing any of the Voyagers did from an imaging perspective is they turned around and took an incredibly boring picture of the solar system where there's a few dots, and they said, we live there. And that was it. Then they shut it off. So Voyager's doing only one thing at this point. It's measuring charged particles. That's it. And every once in a while, we turn every telescope we can find toward the direction of Voyager, and it, using a transmitter with about the power of a refrigerator light bulb, sends back ones and zeros really slow and says, I saw this. And that's it. And I've been at the JPL Command Center, and Voyager's still up on the docket. Every once in a while, we want to know. So they've been happily moving away, and Helios physics people got really excited a few years ago when they said, hey, you know, some of the models say Voyager may be getting to the shock, that termination shock. And if the heliopause is the way we think it is, one of the Voyagers should get there first. And in 2004, and this is the tiny little ones that it's sending back, so several hundred days, it's just moving along, saw this, hey, and then it stays on the other side. That was the termination shock. We actually went through it. We'd gone that far out, we actually went through it. And then, in 2007, it happened with Voyager 2. Voyager 1 encountered it at 94 times as far away from the sun as the Earth. Voyager 2 detected it at 84 times as far away from the sun as the Earth. And if we go back to our map, Voyager 2, Voyager 1, we nailed it. Now, that could almost be the end of the story, except that IBEX continues to work. And IBEX has recently made an interesting discovery that I don't agree with, but I'll report it. And that is that they think maybe things are a little bit slower than we thought. And as a result, this upstream region may not have a shock. It may just slowly decelerate down. And that has all kinds of consequences for all of the models. So people have to go in and say, well, do we still get where Voyager's supposed to be? I don't know. And the other thing, let me see if I've got it here. And what motivates a lot of people to talk about this, oh, I don't have it, more commonly, is that last year, we think Voyager 2 actually crossed the heliopause. It reached another point at about 110 astronomical units, which is about right, where the plasma conditions changed, and every newspaper in America declared that we had entered interstellar space. Maybe. It looks good for that. But even if we have, you know that what we've really entered is this region up here, the pile-up region on one side. We're a ways away from interstellar space. It may be another 100 astronomical units, 100 times farther away from the sun before we truly get out there. And I don't even think even the biggest telescope we've ever built will be able to talk to Voyager by the time it gets there, even if it survives. So we may not actually trace out the full diameter of this feature, but that's where we come into play. That's where we can do more observations from the ground. We're continuing to do our observations. IBEX is continuing to do our observations. But with the help of Voyager, with the help of all of these things, we've mapped out something that you cannot see, that you can barely touch, that's made of things that are so rarefied that you would, if you were a person who worked with vacuums, would think it was the greatest vacuum you'd ever made. And yet, on the scale, the big scale of the solar system, they form a structure that defines the inside regions that we live in. So I'll end there and take any questions that you have. Thank you. Oh, well, ISM is interstellar medium. Yes. And IMF, I guess I forgot to define that one, is interstellar magnetic field. In the red.
Are the frequency and duration of sunspots and solar flares changing from the 11-year cycle?
Over long periods of time, absolutely. Whether we're measuring them changing in a time frame that we can definitively identify? Probably not. The sun obviously is going to produce sunspots following that pattern defined by the rate at which it rotates. And the sun rotates today at about once every 22 days. But that's only a representation of a snapshot in time. We see other stars very similar to the sun that are much younger, and their rotation rates can be 3 or 4 days. So probably early in its history, the sun was rotating much more quickly. This cycle was happening much faster, and in fact, it was probably a more toxic environment to be an astronaut in than the modern world. As time goes by, the sun will continue to slow down, and when it does, that periodicity will change.
Yes, I was just wondering, is there any plans in the future to get some spacecraft out to the heliopause?
Oh, they talk about it. As long as I've been involved in the field, they have sort of on the edge of their planning envelope. It's an Interstellar Explorer, something that's going to go out there. The problem with this type of a mission is it takes so long. And so people tend to get more focused on doing things that are much closer. We will get another chance, actually, to go through both of these boundaries. It'll still take a while, but in 2015, a spacecraft called New Horizons is going to fly by Pluto. And after it flies by Pluto, they're going to hunt for another icy object in the outer solar system and try and fly by that. But afterwards, New Horizons is the fastest spacecraft we've ever built. And it will cross the termination shock, and it will cross the heliopause, and it should still be operating because it's using one of those radioactive generators, and it got there so quickly. So it's actually a really good opportunity to try to take those measurements out to the next level. And while it's not the perfect instrument for that type of measurement, NASA has gotten really good at economizing with what they have, and I think that's probably our mission for the foreseeable future.
Was this actually a part of the Voyager mission to get that far?
Oh, no.
Yeah, I didn't think so. I just wondered about that.
The history of the Voyager mission was that there's a once in a very long while opportunity when the orbits line up so that you could do what we did, which is this grand tour of Jupiter, Saturn, Uranus, and Neptune. And NASA tried to sell the administration on letting them go. The administration didn't really want to pay for a mission that took that long, so they said, well, we'll just go to Jupiter and Saturn. There's no way we'll be able to communicate with the spacecraft when it gets to Uranus. It's too far away. So just fund that. And they got that, and then they got past Saturn and said, hey, look, the telescopes are bigger. How about we go to Uranus? And then how about we go to Neptune? And now how about you not turn it off and we'll go all the way out of the solar system? So Voyager is an accident that we got this. And it's an even bigger accident that we've launched one where when it was done with its tour, it went in one direction, and the other went in the other direction. That would just be the perfect probe of the boundary and the kink in it. So it's a happy accident.
I can talk really loudly.
Okay.
In the space development community, there's a lot of talk about how to protect humans from radiation.
Mm-hmm.
And usually it's about packing materials around them. It would take a lot of material to do it.
Yes, it would.
So what about using a dipole? Is it feasible to have a spacecraft with a dipole strong enough to protect from solar wind and coronal mass ejections and certain kinds of cosmic rays?
Yes. It's great that you mentioned that. There is a group at the University of Washington that I knew when I was there. They have been working on building an electromagnet system for spacecraft that they could create the magnet and then create the plasma, their own plasma, so that they can pack it and create this wall that the solar wind has to fly around. And it has a double use, actually. It's kind of funny because the solar wind, if it's going 1,000 kilometers a second, even though there's not much of it, it has a lot of momentum. And so it turns out that you can make one of these, protect your astronauts, And like a beach ball on the water, it kind of pushes you around. So you can use that magnetic field as a propulsion system, kind of like a solar sail. And so, yes, the answer is you can do that. It takes a lot of energy, though, and so you can't really use solar panels. You really have to have a nuclear-powered spacecraft to do it. Sure.
Okay, you said it's not clear that Voyager is in the interstellar medium. Can you say definitely that Voyager is outside the influence of the sun now?
That is the consensus. Can I say that? If you go and listen to people talk, they will say that it is in the heliopause, may have crossed the heliopause. Whether it is truly an interstellar medium, in the interstellar medium, it's not clear. But of course, leaving the sun's influence would really require that you get so far out that you no longer even know about the boundary. So I could say that it really hasn't left it for that reason. But one of the interesting things about this boundary that we don't really totally understand is that you look at the sun from those pictures that I showed you, it's very dynamic, and every 11 years it's much stronger than it is at the beginning of that time frame. And so we believe that there's pulsations of plasma moving out against this boundary. And so it's possible that Voyager is sitting out there on the other side of it, but 5 years from now, or whatever time frame, we don't know, it might just hop back on the other side. The boundary could move. And so it might go back and forth. So if you want to think about where Voyager is, you can imagine that the interstellar medium is an ocean, and the solar system is a beach, and Voyager is in the surf. And it may be past the waves, maybe not.
I have a question. Some time ago, I heard that the sun was in a big hot bubble of gas.
That would be the local interstellar cloud.
How does that interact with the solar wind?
Through this entire medium. What's happening right now is this, the local interstellar cloud is this it's incredibly rarefied. So if you take a volume the size of a sugar cube, there's maybe one atom in it. So not a lot of material, but it's huge. And it's very hot. It's about 6,000 degrees, which is about as hot as our sun. And we think it's a remnant, a supernova remnant, an old one. And we're moving through it. We used to think 25 kilometers a second, now maybe 23 kilometers a second. You'd think that's not a big difference, but it is. And we're interacting with a part of it that just happens to be close by. So yeah, that bubble, that's where we are.
Does it have magnetic properties,
Indeed it does.
the bubble?
Yes, and that's what's causing that kink, that deflection. If it had no magnetic field, it would be a perfectly symmetric structure.
As a layman, I find all of this very fascinating. Tremendous amount of knowledge that you've imparted tonight. But is this knowledge for the sake of knowledge, or are there practical applications to the knowledge that we're acquiring?
Oh, I think there are huge practical applications to it.
Some examples of that.
Well, the question that I just answered over here. You know, if you go back in time, about 150 years, we did not have a technological civilization. In fact, we had one electric appliance. It was a telegraph. And in 1857, when people were first looking at the sun, they saw an event that they called a flare. And they had seen many flares before, and they said flares always get here about 3 days later, so they were waiting. 12 hours later, that flare arrived. We had auroras in Cuba. People were reading the newspaper by the auroras in the middle part of the United States. Telegraph offices burst into flames. That was the first time we cared about what the sun was doing. And now, we would care a whole lot more. If something like that event, which is called the Carrington event, you can look it up online, they talk a lot of pictures. If that were to happen today, it would probably wipe out the vast majority of our electrical infrastructure, knock out most of the satellites that we have in orbit, ruin this Hubble Space Telescope and probably kill any astronauts that we didn't get off the space station before it hit. So the connection that we have now to a space environment where we're communicating with ourselves through space, and that communication involves our own atmosphere, which is itself supporting charged particles that connect actually to those magnetic fields that respond to the solar wind. All of those things play together. Where you can hear radio stations at night, what types of radio communications you can make, those all play into this. So if we were not technologically savvy, we would probably not need to know much about this. But the fact that we want to go places, that we want to be able to use satellites, that we want to be able to have an infrastructure that makes use of electric forces, requires us to understand this medium in really great and gory detail. And our magnetic field is incredibly complicated. We have studied it better than any other, and it's still hard to understand. This structure is in some ways so simple and so basic that it can give us information that we couldn't have gotten any other way. So it does have practical applications on that level.
Follow up on that. If we knew that was coming, could we do anything about it?
We could unplug our computers, turn off our lights. I'm actually serious about this. The forces involved would drive currents in the wiring systems. That's why the telegraphs burst into flames. So, because remember, it's magnets and electric fields all respond to motions with respect to each other. And so you can generate currents in everything that you've got by that. So we have a lot of safing technologies for spacecraft and other things. We would do our best to put all of them into that state. We would get the astronauts off the space station if we could do it. We'd tell the Hubble telescope to shut off and not do anything until we tell it to do something again, and we would hope. And that's what we'd have to do. We could save a lot, but I don't think there's any way that we could avoid taking some serious damage from one of these. Most of our spacecraft are just not capable of defending themselves all that well. And if you left things plugged in, you would regret it.
The electrical grid?
Yeah, the electrical grid would be seriously affected. You'd have to ask the power company about that. It's possible. I'm sure it's possible to do it. We've never actually tried. We have had solar storms that have wiped out good chunks of the power grid for periods of time, and these were tiny fractions of the Carrington event. I would say that we have the capability and the ability to protect ourselves better than we have, but I don't think we've really appreciated how big the problem might be, and only by looking at these objects or these events happening are we really starting to realize maybe we should be giving it more thought. And hopefully we will be ready the next time it happens. There was recently an observation by a new solar experiment called Stereo that recorded an event that was probably as intense as Carrington that missed us by about 10 days in terms of the placement in the solar system. If our orbit was leading a little further, we would have hit it. And so they published the single most alarming news statistic that no one paid attention to that I'd ever heard, which was, based on that, they estimate there's a 1 in 10 chance of this happening in the next 100 years. So we should probably be planning.
And would that occur on one of these 11-year cycles?
It would probably, it can in theory occur at any point, but it's almost certainly more likely to occur at the peak of that activity, which is the top of every 11 years. We're actually at that peak right now. The good news is that we seem to be on a kind of downward slope. Yes, we're free. We got a decade. I hesitate to say that because then we'll just ignore it for a decade, but yeah, we're probably past the worst part of our danger. Although that thing that was just seen was not long ago, a year or so.
Well, it's wonderful. There's so many questions, and but I think at the moment maybe we'll thank our speaker. And if you have other questions, you're certainly welcome to come up. But thank you very much.
Thank you again.